Welcome to Daily Papers, the podcast where we break down the latest and most interesting academic papers into something you can actually understand. Today we're talking about teaching computers how to see, and not just see, but see more like we do. Because it turns out the way most AI sees the world right now is, well, it's a bit brute force.
That's putting it mildly. Imagine you open a photo on your phone. How do you look at it? Your eyes don't just absorb every single pixel in one go. They dart around, right? You look at a face, then maybe a sign in the background, then a funny dog in the corner. You build up a picture of the scene piece by piece.
Exactly. But that's not how most computer vision models work. They take the entire image, every pixel from the most important detail to the most boring, blurry corner, and they process all of it at the same time with the same amount of effort.
This has led to what the authors of today's paper call the impossible triangle of computer vision. Picture a triangle with 3 points. On one point, you have high-quality inputs like high-resolution images and videos. We want our AI to be able to see the world in detail.
On the second point, you have large, powerful AI models. Generally speaking, bigger models are smarter and more capable, so we want those too.
But the third point of the triangle is efficiency. We need these systems to be fast and not use a ton of energy. Think about a self-driving car. It needs to react instantly to a pedestrian. Or even just your phone. You don't want an AI feature to drain your entire battery in 5 minutes.
And here's the problem. With the current process everything at once method, you can't have all three. If you use big models and high-res images, you kill your efficiency. The computer's energy bill goes through the roof and it takes forever. It's a massive bottleneck.
So this paper, titled Emulating Human-like Adaptive Vision for Efficient and Flexible Machine Visual Perception, proposes a new way forward. And the solution is right there in the title. Let's teach the machines to see like humans.
Let's talk about how we see. Our eyes have a tiny central region called the fovea, where our vision is super sharp and detailed. Everything else in our peripheral vision is much blurrier. So to see a whole scene clearly, we have to move our eyes around in quick jumps called saccades. We focus on one small point of interest, then another, then another.
This paper builds an AI system that does exactly that. It's called adaptive NN. Instead of processing the whole image at once, it takes a much smarter step-by-step approach.
First, it takes a quick, low-resolution glance at the entire scene, just to get the general gist of what's going on, like we do when we first walk into a room.
Then, based on that blurry glance, a part of the model called the vision agent decides, okay, what's the most interesting or important thing to look at more closely? And then it directs its gaze to that small patch of the image.
This gaze is what the paper calls a fixation. The model processes just that small, high-resolution patch, gathering detailed information from it. Then it adds this new info to its memory of the scene.
And here's the really clever part. After each fixation, the vision agent asks itself a critical question. Do I have enough information now to complete my task? The task could be anything from, is there a cat in this photo, to what does that street sign say?
If the answer is, yes, I'm confident, it stops looking and gives the answer. This saves a huge amount of energy. If the answer is no, I'm still not sure, it goes back and picks another spot to fixate on, gathering more information. An easy, clear image might just take 1 or 2 fixations. A complex, cluttered one might take 5 or 6.
So it's not just a new architecture, it's a whole new paradigm. A shift from passive vision, which just takes in whatever you give it, to active vision, which intelligently explores a scene.
So the big question is, does it work? Is it actually better?
The results are pretty staggering. In some tasks, particularly complex ones like identifying tiny traffic signs in high-resolution images taken from a moving car, adaptive NN was up to 28 times more computationally efficient than a traditional model.
28 times. That's not a small improvement. That's the difference between a feature being a cool demo in a lab and something you can actually put in a real car.
And it's not just efficient, it's also flexible. You can actually tell the model what your budget is. If you have plenty of power, you can let it take more fixations to be extra accurate. If you're running on a low battery, you can tell it to be quicker and use fewer fixations. And you don't even have to retrain the model to do this.
One of the coolest applications they tested was in medical imaging. They trained the model to detect pneumonia from chest x-rays. Now, the model was only ever told, this image has pneumonia, or this one doesn't. It was never told where the pneumonia was.
But because adaptive NN shows its work, you can track its fixations. You can literally see where it's looking. And the researchers found that the model learned to focus its gaze on the exact same regions of the lung that human radiologists had marked as showing signs of pneumonia.
That's incredible. It not only gets the right answer, but it gets it for the right reasons. That builds a ton of trust, which is crucial for using AI in high-stakes fields like medicine. It's what we call interpretability. We can interpret why the AI made its decision.
But the most mind-bending part of this paper, for me, was the visual Turing test they ran.
Right. The Turing test is the classic test for AI, where a human has to judge if they're talking to another person or a machine. This is the visual version of that.
They showed human judges two different sets of viewing patterns on an image. One was generated by a real person's eye tracking data, and the other was generated by adaptive NN. The judge's task was simple. Tell us which one is the machine.
And they couldn't do it. The accuracy was about 50%, which is the same as just guessing randomly. The AI's way of looking at the world was, in many cases, indistinguishable from a human's.
And that has some profound implications. It suggests that this very complex, efficient, and seemingly intelligent way of seeing the world doesn't necessarily have to be hardwired into our brains from birth.
This model learned these human-like behaviors simply by being trained to recognize objects efficiently. It suggests that the strategy of active adaptive vision might just be the most logical solution to the problem of seeing a complex world with limited resources.
So this paper gives us more than just a faster, more flexible AI. It gives us a new tool for understanding ourselves and a glimpse into a future where machine vision is much less brute force and a whole lot more human.